Welcome back to ByteLearn. Last video, we traced an order on Swiggy from your phone to a server in Bengaluru, DNS, TCP, HTTP, load balancer, Redis. But there was one layer we only glanced at, the most important one, the layer where everything that actually matters is stored permanently. Here is a number worth thinking about. Right now, someone in India is booking a train ticket on IRCTC. The moment they click confirm booking, the available seat count on that train drops by one. Permanently, irreversibly guaranteed not to sell to anyone else all in under 100 milliseconds, even during the Tatkal rush when lakhs of people are trying to book simultaneously. How does that work? A database. And specifically, a database designed to handle exactly that kind of pressure. Databases are not just a backend detail, they are India's institutional memory. Every PhonePe payment you have ever made, stored in a database, your Aadhaar record, linking your biometric identity to your bank account, your gas subsidy, your vaccination record in a database. India's entire digital identity stack runs on this technology. Understanding databases is not optional for anyone who builds software, it is foundational. In this video, we are going to cover what a database actually is and why it exists. We will understand why keeping data in RAM is not enough and what persistence actually means. We will cover SQL databases and what makes them reliable for financial transactions. We will cover NoSQL databases and when their flexibility beats SQL structure. We will give you a decision framework that maps directly to system design interviews, and we will show you exactly where the database fits in the architecture you learned last video. This video is built for two people. If you are learning backend development and the database layer has always felt like a black box, this is how it clicks. And if you are preparing for system design interviews, this is critical knowledge, SQL versus NoSQL ACID properties, when to choose which database. These questions come up in almost every system design round at any serious company. And stay till the end. After we cover the foundations, I will show you a 3-question decision framework for choosing between SQL and NoSQL for any system. It is the single most actionable takeaway in this video and exactly what interviewers are looking for when they ask you to design a system. Do not skip it. One quick note, this video builds directly on the client-server architecture we covered last time. If you have not watched that video yet, the link is in the description. I will reference the client-server, load balancer and Redis cache as we build the full picture here. Everything will still make sense, but the mental model is richer if you have seen both. Here is the fundamental problem every application faces. When your app is running, it stores everything it is currently working on in RAM. Random access memory, RAM is incredibly fast. A read from RAM takes around 100 nanoseconds. That is why your app feels snappy. But RAM has one critical weakness. When the power goes off, when the server crashes, when the process restarts, everything in RAM is gone. This is not a software bug, it is a hardware property. RAM requires continuous electrical power to maintain its data. The moment that power is interrupted, a server crash, a kernel update, a hardware failure, everything in RAM is gone. For a bank, that would mean every pending transaction disappearing. For IRCTC, it would mean losing every booking made since the last restart. This is why applications cannot rely on RAM alone. What we need is storage that works differently. We need data to survive power loss, server restarts, and hardware failures. We need the same data to be accessible to thousands of users simultaneously. We need to be able to find any specific record, your PhonePe transaction from 6 months ago, in milliseconds, not hours, and we need guarantees. If a payment is marked completed, it must be completed with no exceptions. A database is a system, software, plus the storage it manages, that stores data persistently, organizes it for fast retrieval, and handles concurrent access safely. It is not just a file on disk. Files on disk are slow and unindexed. A database adds structure, indexing, and guarantees on top of disk storage. Those guarantees are what make a bank account balance trustworthy and a train seat booking reliable. Today, there are two major families of databases. SQL databases, also called relational databases, store data in tables with rows and columns, enforce strict schemas, and provide strong ACID guarantees. NoSQL databases take a different approach: flexible schemas, horizontal scalability, and eventual consistency. Each family has strengths the other lacks. Choosing between them is one of the most important decisions you make when designing any system. Both families are trying to solve the same fundamental problem: store and retrieve data reliably, but they make opposite trade offs to get there. SQL optimizes for consistency and query power. NoSQL optimizes for flexibility and scale. By the end of this video, you will know exactly when each wins and be able to defend your choice in any system design interview. Let us trace exactly where data lives as it moves through the stack. You open PhonePe and check your transaction history. Your app, the client, makes an HTTP request. The request travels across the network to PhonePe's application servers. The application server receives your request. It begins processing, validating your auth token, building the database query. Right now, all of this is happening in RAM, the server's working memory, blindingly fast. Before hitting the database, the server checks the cache, Redis in most production systems. If your recent transaction history is already cached from a previous request, the cache serves it back in about a microsecond. No database involved. Cache miss: the data is not cached or the cache has expired. The server now queries the database. This is the slow path, roughly 20 milliseconds for a well-indexed query. But the data is guaranteed to be there exactly as it was written, no matter how many times the server has restarted since. The database stores data on disk, traditionally spinning hard drives. Now high-speed SSDs in modern systems. When you write to a database, the data is flushed to disk. When the server crashes and restarts, the database reads from disk and all your data is exactly where it was. This is persistence. The database returns your transaction records. The app server packages them into a JSON response, caches them in Redis for future requests, and sends the response back to your phone. Now think about the right path. You tap send on PhonePe. This is where the database's persistence guarantees become life or death. The app server receives your payment request and must write it to the database, not to RAM, not to cache, directly to disk with a hard guarantee. The database commits your transaction, writes the debit and credit to disk with a guarantee called durability. The moment that commit succeeds, even if every server in the data center crashes in the next millisecond, your payment is safe. It will be there when the servers come back up. That guarantee is what makes financial databases trustworthy. SQL databases have been around since the 1970s. They power most financial systems in the world: your bank, PhonePe, Google Pay, IRCTC, almost every system where data integrity is non-negotiable. SQL stands for Structured Query Language, the language you use to interact with them. But SQL is really about the relational model underneath. A SQL database organizes data into tables, like spreadsheets with predefined columns. An accounts table has columns like account ID, user ID, and balance. A transactions table has transaction ID, from account to account, amount, and timestamp. Every row follows the same structure. This strict schema is not a limitation, it is a feature. It prevents bad data from ever being stored. The relational part of the relational model is what makes SQL powerful. Tables can reference each other. A transactions table references the accounts table. When you query PhonePe for your last 10 transactions, a SQL join fetches both tables and returns exactly what you need in one query. No extra network calls, no stitching data together in application code. Let us trace a PhonePe payment. You tap pay 500 rupees to a friend. Your app sends an HTTP post request to PhonePe's API server. The API server begins a database transaction, a formal unit of work. Everything that happens next, either all succeeds together or none of it happens. This is atomicity, the A in ACID. No partial payments, no balance disappearing without a record. The database runs two SQL update statements. One debits your account by 500 rupees. One credits your friend's account by 500 rupees. These two operations are wrapped in a single transaction. If the debit succeeds but the server crashes before the credit, the entire transaction rolls back. You keep your money, your friend gets nothing, but nobody loses anything. Both statements succeed. The database commits, writes permanently to disk. The API server returns HTTP 200 to your phone. The green tick appears. Every step of this used the SQL relational model to guarantee your money went exactly where it was supposed to go, with zero chance of a half transaction existing. SQL wins when your data has clear relationships, when you need ACID transactions, when your schema is stable, and when you query data in complex ways, joins, aggregations, filters across multiple tables, banks, payment systems, booking platforms, ERP systems, hospital records, anything where data integrity is not negotiable. IRCTC uses SQL because if two people try to book the same seat, the database must catch it and reject one. That is a SQL level constraint, not something you want to handle in application code. Now let us talk about NoSQL. The name is misleading. It does not mean NoSQL ever. It means not only SQL databases that do not use the relational model. NoSQL databases traded SQL's strict structure for flexibility and horizontal scalability. And for many of today's largest applications, that trade-off is exactly right. The most common NoSQL type is a document store. Instead of tables and rows, document stores hold JSON objects. Each document can have a different structure. A restaurant in Swiggy's catalog might have a menu with 50 items, dietary tags, photos, and real-time availability data, all in one document. In SQL, that would require 5 joined tables. In MongoDB, it is a single document fetch. Another type is key value stores, exactly what the name says. A key maps to a value. Redis is the most famous example. Your session token is a key. Your user data is the value. PhonePe's UPI pin attempt counter is a key value entry. Swiggy's restaurant listing for your city is cached as a key value pair with a TTL. Key value stores are the fastest database type because the lookup is OVL1 constant time regardless of database size. Let us trace how Swiggy uses NoSQL for its restaurant catalog. You open Swiggy in Bengaluru, your request hits a load balancer, then reaches an app server. The app server queries a NoSQL database for all restaurants near your location. Each restaurant is a document, menu items, photos, delivery times, ratings, all nested in one place. One query, one fetch, one response, no joins needed. The NoSQL database finds all nearby restaurants in milliseconds using a geospatial index and returns them as a list of documents. The app server serializes them to JSON and sends them back. Swiggy can add a new field, say sustainability rating or allergen tags, to restaurant documents without a database migration. Every document can have different fields. This flexibility is exactly why Swiggy chose NoSQL for the catalog. In SQL, adding a new column to a table with 50 million rows is a slow, risky migration. In NoSQL, you just start writing the new field. NoSQL wins when your data structure varies across records, when you are scaling horizontally to handle millions of writes per second, when you do not need complex joins, and when eventual consistency is acceptable. Swiggy restaurant catalogs, Hotstar video metadata, Twitter's tweet store, Google's search index, these are all NoSQL use cases. The key phrase is eventual consistency. NoSQL databases relax the strict ACID guarantees of SQL in exchange for better performance and scale. When you use a SQL database for financial data, you are relying on 4 guarantees known as ACID. These are the properties that make a database transaction trustworthy. Without ACID, you cannot build a payment system, a booking platform, or a medical record system. Let us go through each one with a real example. Atomicity means a transaction is treated as a single indivisible unit. When you send money via PhonePe, two things happen. Your account is debited and your friend's account is credited. Atomicity guarantees that if anything fails between those two steps, the whole transaction is rolled back as if it never happened. No half transactions, no money disappearing. Either both happen or neither does. Consistency means the database enforces all defined rules on every transaction. If a rule says an account balance cannot go below zero, the database will reject any transaction that would cause it. Even if your app code forgot to check IRCTC seat count cannot go below zero because the database enforces that constraint. No seat is ever double sold because the database prevents it at the storage layer, not just the application layer. Isolation means concurrent transactions are invisible to each other until they commit. During IRCTC Tatkal at 10 am, lakhs of people are booking simultaneously. Isolation ensures two users never see the same seat as available at the same moment. Each transaction sees a consistent snapshot of the database. This prevents dirty reads, where you read data that another transaction is still modifying and might roll back. Durability means that once a transaction is committed, it is permanent. If the database sends you a commit acknowledgement and then the data center loses power, when the servers come back online, your transaction is still there. This is achieved through write-ahead logging. Every change is written to a persistent log before being applied to the main data files. The wall ensures no committed transaction is ever lost, even in the most catastrophic failure. Every time you make a UPI payment, book a train, execute a trade on Zerodha, or your doctor accesses your hospital record, ACID properties are working silently behind the scenes. 2 billion PhonePe transactions a month. Every single one atomic, consistent, isolated, and durable. No money ever disappears. No seat ever gets double booked. No prescription ever points to a patient who does not exist. That is SEID guaranteeing the integrity of India's digital infrastructure. The tension between SQL and NoSQL comes down to one fundamental trade-off: consistency versus scalability. SQL gives you strong guarantees but is harder to scale. NoSQL gives you flexibility and scale but relaxes some guarantees. Neither is better. They are optimized for different problems. When an interviewer asks you to choose a database for a system, use three questions. First, does this data need ACID transactions? If money or legal records are involved, always choose SQL. Second, is the schema fixed or variable? Financial transactions have a fixed schema, SQL. A social media post with optional photos, videos, polls, stickers, variable schema, NoSQL. Third, how do you need to scale? If you can scale vertically, SQL works fine. If you need to scale horizontally across hundreds of nodes, NoSQL is designed for that. Here is the insight that separates candidates in interviews. Real production systems use both. Swiggy uses SQL for orders and payments and NoSQL for its restaurant catalog. Hotstar uses Cassandra, a NoSQL column store, for watch history where millions of users are writing simultaneously, and MySQL for billing where ACID matters. PhonePe uses PostgreSQL for the transaction ledger and Redis for session management. The right answer is almost never only SQL or only NoSQL. The right answer is SQL for the parts that need ACID, NoSQL for the parts that need scale. To summarize the framework in one line, if the data needs ACID and has a stable schema, use SQL. If the data needs flexible schema and horizontal scale, use NoSQL. And in any real system, the answer is almost always both different databases for different parts of the same application. Every strong system design candidate knows this. Now you do too. And here is where the database fits in everything we have covered across both videos. Client makes a request, load balancer routes it, app server processes it, Redis cache is checked first for reads. Database is the source of truth for everything. Permanent SQL for the data that cannot afford mistakes. NoSQL for the data that needs to scale. This is the complete picture. Let us trace an IRCTC ticket booking end to end across every layer. This is the full stack from your tap to the database write. You tap book ticket on IRCTC. Your phone builds an HTTP post request, passenger details, train number, class, date. DNS resolves irreversible to an IP. TCP handshake opens the connection. TLS encrypts the channel. The request arrives at IRCTC's load balancer. The load balancer checks which app servers are healthy and routes the request to one with capacity. This is exactly the layer we covered in video 1. The load balancer as the gatekeeper distributing traffic across the fleet. The app server first checks Redis. Is current seat availability for this train already cached? Seat data is cached with a short TTL, maybe 30 seconds, to avoid hammering the database on every search request. For a search, this is the fast path. For the actual booking, not a search but a confirmed purchase, the cache is bypassed entirely. The app server connects directly to the SQL database and opens a transaction. This is the right path. Real money, real seats must go to the database. The database runs a select for update on the specific seat. This locks the row. No other transaction can claim this seat until this one completes. Even if 10,000 people are trying to book the same seat at Tatkal time, only one will get the lock. The other 9,999 will wait their turn. Booking confirmed. Seat count decremented. Payment record written. Commit issued. All permanent on disk. The database acknowledges success. The confirmation travels back database to app server through the load balancer across the network to your phone. Your IRCTC app shows the ticket. That seat is yours. The entire journey, every layer completed in under 2 seconds. Client server architecture from the last video handles the network. The database layer you just learned handles persistence. Together they are the foundation of every app you use. DNS found the server. TCP connected reliably. The load balancer distributed the load. Redis cached the seat search. SQL guaranteed. The booking was atomic and durable. Every layer doing its specific job. That is system design. Before digital databases existed at scale, every important record was kept on paper. Bank balances were written in physical ledgers by hand. Train reservations were in handwritten registers at each station. Patient records were in paper files that could be lost, damaged, or simply illegible. Land records in district offices were the source of endless litigation because they were incomplete, inconsistent, and manipulable. The database changed all of this, not overnight but irreversibly. Consider Aadhaar, a single database, 1,400,000,000 records, each containing a biometric fingerprint, iris scan, and identity information, is the foundational layer of India's entire social infrastructure. Gas subsidies go directly to the beneficiary's bank account because the Aadhaar database links their identity to their account. Vaccination records are linked, pension records are linked. 300 million people who never had a bank account now have one because Aadhaar let them prove their identity digitally. One database, 1,400,000,000 lives made more legible to the systems that serve them. Think about what changed for the 300 million people who work far from home. Before UPI and the databases behind it, sending money to family meant going to a bank branch, filling out a demand draft form, paying a fee, and waiting 2 to 3 days. Now it takes 2 seconds on a 7,000 rupee phone. The database handling that transaction, verifying the sender's balance, recording the debit, recording the credit, ensuring atomicity, maintaining the SCID guarantee is the reason that is possible. A migrant worker in Surat can now send his entire month's earnings to his family in Bihar in less time than it takes to read this sentence. India's response to the COVID pandemic was run on databases. COVID tracked 800 million vaccinations across every PIN code in the country. Real-time bed availability across hospitals, databases. Resource allocation for oxygen concentrators, databases. When India announced free vaccines for everyone, the system had to handle tens of millions of registrations in days without losing a single record. That worked because the database layer was designed for exactly this kind of pressure. Here is the deepest insight about databases. In the physical world, something becomes real when it happens. When a note changes hands, when a deed is signed, when a doctor sees a patient. In the digital world, something becomes real when a database commits it to disk. Your UPI payment does not exist until the database commits it. Your IRCTC booking is not real until the seat record is updated and committed. Every software engineer who builds systems that matter needs to understand what that means and respect the guarantees that protect it. You just covered one of the most critical concepts in all of software engineering, the database layer. You now understand what persistence actually means, why RAM is not enough, how SQL databases use the relational model to guarantee ACID properties, how NoSQL databases trade structure for scale and flexibility, and how to make the SQL versus NoSQL decision. Most developers work with databases every day without understanding why they work. Now you do. Here is what you can now do. You can explain ACID properties with real examples, not just define the acronym. You can apply the three-question framework to any system design problem and defend your database choice. You can trace a complete request from the users tab through the network, the load balancer, the application server, Redis cache, all the way to the SQL or NoSQL database and back. You can answer every standard database question in a system design interview. The next video in the series, Distributed Systems Explained, we just learned that one server handles client-server architecture and one database stores the data. But for Hotstar to stream to 50 million simultaneous viewers, one server is not nearly enough. One database is not nearly enough. The next video covers why, how you scale beyond one machine, what vertical versus horizontal scaling means, and what happens when things fail, as they always do at scale. Link is in the description and pinned in the comments. If this video gave you a clearer mental model, if the persistence problem made sense, if ACID properties clicked, if the SQL versus NoSQL framework is something you will actually use, then subscribe to ByteLearn. Every week, we go deeper on system design concepts, data structures, and how real Indian applications are built. Hit subscribe and the bell so you do not miss distributed systems next Tuesday. And before you close this, leave a comment. Tell me which concept landed for you. Was it the ACID properties explained through PhonePe? The select for update, locking out 10,000 concurrent IRCTC bookings? The three-question framework for choosing between SQL and NoSQL? Or drop me a question about the next video. Distributed systems, scaling, what happens when the database itself becomes a bottleneck? I read every comment and replied to every genuine question. Your comment might be the next video.